Okay, now what I would like to do is show you something extremely interesting. I think you are going to like this very much, and this would be very useful in our understanding of fluid mechanics. So, I want to show you the role of the velocity gradient in the curl of the velocity as well as the strain rate tensor that we have derived. Okay. So, let us start with gradient of V. So, if you recall, the gradient of V tensor was actually given as del Vx by del x, del Vx by del y, del Vx by del z. Then I had a term here del Vy by del x, del Vy by del y, del Vy by del z, and then the last row was del Vz by del x, del Vz by del y, del Vz by del z. And this is arising because the velocity field that I have in this 3-dimensional space is changing with x, y and z. Okay. If it is a uniform flow, then you would see that this gradient of V becomes 0, and then of course, these elements would simply translate and not deform or rotate or do anything. So, that is a very bland kind of a flow, not very interesting. But if the gradient of V is non-zero, then I get a scenario like this. Now, this tensor, as I had explained you, can be split into two parts. So, gradient of V can be split into two parts, a symmetric part and a skew symmetric part. So, if you remember, we had done this in an earlier lecture. So, this is the symmetric part, which I simply take the transpose of this, add to it and then take the average of the two. And then there is another part which is the skew symmetric part. Right. So, this is the skew symmetric part. This is an identity. In fact, you can see that these two terms cancel out, and these two are the two halves which again get you the gradient of V. Okay, so, now I am going to write down this into a symmetric part and a skew symmetric part. So, this will be a little messy, so please forgive me for that, but I think it is rather educational, so I will still go ahead with it. So, therefore, let me make these two matrices here. So, this would be the symmetric part and this would be the skew symmetric part. All right, the symmetric part. So, of course, this guy stays as it is. So, I have del Vx by del x. So, the diagonals do not change. Diagonals do not change at all. Okay. Let us talk about this term over here. So, I would get here half of del Vx by del y plus del Vy by del x. And over here I would get a term which is half of del Vx by del z plus del Vz by del x, right. And because this is symmetric, so I am going to just say that this term comes over here and this term would actually come over here. And I now need to fill in these two terms, which I will, which actually would be this term plus this term, half of that. So, this would be Vy by del z plus del Vz, and I would say the same term would fill up that location. So, I only need to fill in 6 of the terms, the 3 diagonals and the upper triangle, and then the lower triangle I should be able to simply get from the symmetry. What about the skew symmetric part? Clearly, these terms would be 0, right? And I can go ahead and write down this term. In fact, this would be just if I take these 2 terms, so I should be able to write this down. So, this would be half of del Vx by del y minus del Vy by del x. So, that is I would get by doing this and the transpose of this and the half of that. The next term here I could simply write it as half of del Vx by del z minus del Vz by del x. And over here this would be simply negative of this term because it is a skew symmetric matrix. Similarly, this here would be simply negative of this term that I write. And over here I would now fill up as del Vy by del z minus del Vz by del y, and over here I would get simply negative of this term. Okay, what do we get out of all this hard work? Well, if you look at this guy over here and my strain rate tensor, okay, you would see that they are actually identical. Okay. So, this actually corresponds to E of the strain rate tensor. So, the symmetric part of the gradient of V actually corresponds to the strain rate tensor. And what about the skew symmetric part? If you recall, my curl of velocity that was given as omega, and if you recall my rotation, that was half of omega. And let me recollect for you, you should have it in your notes, what are my omega x, omega y and omega z. We worked these out just a minute ago. So, my omega x is half of del Vy by del x minus del Vx by del y. This is half of del Vx by del z minus del Vz by del x, and this is half of this one is omega z, and I could now write omega x here. So, this is Vz by del y minus del Vy by del z. And I would like you to identify this term over here. Do you see that the two terms? So, this is something like minus omega z, and this term over here Vx by z is something like omega y, and this term over here Vy by Vz is minus omega x. So, actually this matrix here I am able to write it as 0, 0, 0. This is minus omega z, omega y, this is minus omega x, and because it is skew symmetric, so this one is omega z, this one is minus omega y, and this is omega x. So let me summarize to you what this spectacular result shows us. If you give me a velocity field, I can compute the gradient of the velocity field. That means, how do, taking the three components Vx, Vy, Vz, how do the three derivatives in the x, y and z direction they change. And these can be written as sum of two quantities. One is the strain rate tensor and the other is the rotation. Remember, the rotation was of a fluid element rotating about its axis. So, omega z means it is rotating about the z axis in the xy plane, and likewise I could argue for omega y and omega x. So, this is what the fluid kinematics can tell us. We have not used any concept of a force till now. Simply working with the velocity field, I was trying to figure out what happens to this fluid element. So, what we have been able to see is the fluid element could go through a strain rate. The strain rate could be of two kinds. It is either extensional or rotational. The extensional is given by the diagonal, okay, these three terms. These off diagonal terms tell me the shear strain rate of the element, and the skew symmetric part is simply telling me about the rotation. So, this is an absolutely fascinating decomposition. I would now like to show you what a real fluid element would go through in a certain kind of flow. So, let me give you an example. So, I want to show you with a very simple example what does a typical fluid element go through. So, imagine that I had a velocity profile of something like a boundary layer. So, this is a solid surface, and this is a velocity profile. Let me call this as Vx. Assume Vy is 0. This is just for simplifying. So, things are only along the x direction, and although this is not a great assumption, but just for explaining you the concept, we forget about the velocity in the y direction. And I would like to see what happens to these fluid elements with time. So, what I will do is, I will take a fluid element, let us say over here, and I would take a fluid element, let us say somewhere over here. So, this is at t equal to 0. And then I want to see what happens at t equal to delta t. So, maybe I use a different color. So, at time delta t. Notice when I come to this element here, the speed on the surface is 0. So, this element actually stays here, does not go anywhere, this edge. On the other hand, these two edges, they move to the right with a speed which is the local speed times delta t. But I am saying that the flow has same speed everywhere along x. So, there is no change along x, there is only change along y. So, both these points move with the same speed, and therefore, I get an element like this. What about this one? Well, these two are roughly the same. So, this moves by a certain amount, maybe I should put it here. This moved by a little bit, not very different. and therefore I get a shape almost like this after time delta t. In fact, they are identical. So I have assumed that there is very little difference between the Vx at this point versus this point. They are virtually the same, very minor difference, but there is a very big difference at the lower part of the boundary layer. All right. Let us try to see what happens at 2 delta t. And this guy goes even further down. And this one over goes maybe something like this. Three delta t. And you would see this fellow goes something like this. And this one over here maybe. And the final picture I want to show you is maybe at 4 delta t. And there you would see so you can imagine the state of this element. It started off with a very nice rectangle, and after a long time it deforms into a needle-like element. So I could ask myself that based on the analysis I have done so far, what exactly is this element going through? And you would notice that this particular element goes through a rotation, because it is rotating. Okay, this edge is fixed, but the vertical edge is tilting in the clockwise direction. So it is definitely going through rotation. It is also going through a shear deformation. So there is definitely a shear strain rate, and there is a rotation rate. Okay. Whereas here the flow is largely only translational. Because we are outside the gradients. Okay. Here the gradients are small, here the gradients are small at the top, the gradients are large here. So you would get a rotation rate and a shear strain rate, but here the flow behaves as if it is almost like a uniform flow. Okay. So one thing that I wanted to draw your attention to is that when you get to a flow close to the wall in a viscous flow, then you are going to get even rotation. So even though the streamlines would look straight, horizontal, but this flow is going through enormous rotation, local rotation. So the concept of rotation in fluid mechanics has to be kept in the correct context, otherwise you may lead to it may lead to some erroneous kind of understanding. So if I look at the gradient of V tensor, this I could split into a symmetric part and a skew symmetric part. And this, let me remind you, was simply half of gradient of V plus gradient of V transpose. And the skew symmetric part was half of gradient of V minus gradient of V transpose. This we refer to as the strain rate, and we call this as the strain rate tensor, which has again 9 components, but because it is symmetric by definition, this is the symmetric part. Therefore, there are only 6 independent components. So if you recall, E was something like a matrix which had some terms over here, and then this part is actually the same as this part over here. Right? So that's the symmetric part. Okay. The skew symmetric part we said is related to rotation of a fluid element. So I am not going to go into the details again, but we said that this is somehow related to the rotation vector. And this, as you recall, was same as half of omega, which is vorticity, which actually corresponds to the curl of velocity. Okay, so to put things in perspective, if I have a velocity field, then it's going to change at different points in my domain. So I am referring to this plane of the blackboard as a 2-dimensional domain. And I could talk about a component that causes a spin of a fluid element, a rotation about its axis, and something that causes a strain rate. And as I showed you in the last class, the strain rate could be extensional, okay? It could be angular in the sense of shear, and so on. Now we would like to relate it to stress. So the idea is, can I relate the gradient of velocity field, which actually results in something called a strain rate, to stress, which then would be able to give me some kind of a force balance, which I am really interested in. So there are various models of this stress and strain rate relationship. So we are talking about stress versus strain rate. Okay? And this would really depend on what kind of fluid that we have. So blood, for example, would behave a little bit different than something like a fluid which is highly non-Newtonian, maybe like tar, okay? And so on and so forth. So we are going to look at the simplest, or rather a simple fluid. And a model of that is a Newtonian fluid. Okay? You could have many kinds of fluid, but Newtonian fluid is one simple model. And here the idea is that stress is directly proportional to strain rate. Okay, it's a linear relationship. So for example, when you look at solid mechanics, or you may have studied in your high school, the Hooke's law, which says that stress and strain are related in the sense that stress is directly proportional to strain. And then you have the proportionality constant, which is the coefficient of elasticity, the Young's modulus. So in fluid mechanics, we cannot talk of just strain, we talk of a strain rate, but the simplest fluid would have that the stress is generated by strain rate. Okay? And you can see that if I have a velocity field which varies in space, rotation in this kind of a scenario will not add to the stress. Okay? So it is only the symmetric part which is the strain rate. So, here is a model that is I would like to give it to you. So, if I call stress as tau, then this is minus pi plus twice of mu times epsilon. So, that is a Newtonian fluid. So, this is the pressure part, of the stress, and this here is actually the strain rate, and mu here is the coefficient of viscosity. And there are various methods by which you can characterize the viscosity of a fluid. There are certain equipment that you can use, for example, a rheometer, where you can estimate what is the coefficient of viscosity, and it would be different for different fluids. Okay. So, let me recall for you that pressure was something that we said acts normal to the surface of a fluid element, and therefore, it actually acts only along the diagonals of tau. So, it only contributes to normal stress, and the negative sign means that it is compressive in nature. Okay. So, if I take a fluid element, if this is my fluid element, then we know that the pressure is same in all directions, that is the Pascal's law, and it is compressive in nature. If you remember, so this is P, and if you remember, the convention for tau that we followed is that this is tau xx. So, it is positive in the positive x axis on the positive x face, and of course, here it would be pointing in the other direction. This would be tau yy, and then we had these shear stresses. So, this is tau xy, x face y direction, and this one is the y face, but the x direction. And likewise, I could name these as well. But we already know that tau yx and tau xy are going to be equal. So, we have already looked at these things. All right. So, in the Newtonian fluid, so if I do in 2D, then a Newtonian fluid would look something like this. So, that would be the state of stress would be given by a 2 by 2 matrix, because it is 2 dimensional. In 3D it is 3 by 3, and this entry is going to be minus P plus del Vx by del x. This one would be minus P plus del Vy by del y. And over here, I would simply have mu times, sorry, there would be a mu here. I am sorry, guys. So, that is the coefficient of viscosity. And then, as far as the shear strain rates are concerned, they would contribute to mu times del Vx by del y plus del y by del x. And likewise, this term here would be del Vy by Vx by Vy plus del Vy by Vx. Normally, we call these quantities as normal stresses, and then this guy over here and this guy over here, these are the shear stresses. Okay, so let me now kind of summarize what we have been able to do. So, we are finally interested in stresses because these would relate to the forces acting on a fluid element. But then we also have the strain rate, and that arises essentially from the velocity being different at different points in the flows. So, we have now been able to propose a model, in this case a very simple model, that stress is directly proportional to strain rate. You could ask why why just strain rate, why not the square of that, okay, why not the cube of that? Sure, that is possible, and that would be a different model. Okay. And so, for the purpose of this course, this is the model that we use. This relationship between stress and strain rate is also known as a constitutive model or a constitutive relationship. All right, so we will leave it at that, and we will return back to it when we talk about force balance. But I want to start a different topic right now, and maybe just a small clarification so that you can relate to what we did in an earlier class. Suppose I look at a very special case. So, I look at tau xy, which is mu del Vx by del y plus del y by del x. So, I am talking about special case in 2D, and let del Vy by del x tend to 0, or it may be very small compared to the quantity over here. Then we could approximate this as mu del Vx and del y. And this is the Newton's law of viscosity that we looked at earlier in the course. So, that was a very special case, and this one is a more general case. Okay. So, now you are able to relate to what we described a fluid in the first few lectures, and then what a Newtonian fluid in general is.